Car moving along a curved road. Earth revolving around sun.
All are examples of circular motion.
We begin a very important chapter for your JEE preparation. Circular motion. We will build it slowly and carefully, so that every formula you use is a formula you actually understand. But before we can run on circles, we must walk on straight lines. So let us start with the simplest question of all. When does velocity change? Look at the straight road. A car is moving along it, and its speed is held constant. To see what that means, I am dropping the dot at the car's position after every equal interval of time. Now look at the dots. Equally spaced, equal distance covered, and equal time. That is constant speed. And since the road is perfectly straight, the direction of motion is also constant. Now think about the velocity. Velocity has a magnitude, which is the speed, and it has a direction. Here, the speed is constant, and the direction is constant. Both ingredients are fixed, so the velocity is constant. Nothing about this motion is changing. Now watch a second car on another straight road. Same kind of road, same direction, but this time, the driver presses the accelerator. Again, I drop a dot after every equal interval of time. And now look at the spacing. The dots are spreading out. The car covers more and more distance in each interval. The speed is increasing, while the direction stays constant. So here, the magnitude of the velocity is changing, even though the direction is not, and that alone is enough. The velocity is changing, and that is the headline of today's lesson. On a straight road, velocity changes as speed changes. But hold on to the spot. Is changing the speed the only way to change a velocity? What if the road itself begins to bend? That is exactly where we are going next. Now students, let us return to the question we ended with. Here is the same car, and the driver is just as disciplined as before. The speedometer is lot. The speed is constant. I'm again dropping dots after every equal interval of time, and you can see they are equally spaced along the road. But there is one big difference now. This road is not straight, it bends. Watch the direction of motion. At every point, the car points along the road. Here, it moves this way. Here, this way. And here, this way again. All these arrows have the same length, because the speed is the same everywhere, but they point in different directions. So on this road, the direction of motion is continuously changing. Now recall what velocity is made of: magnitude and direction. The magnitude, the speed, is constant, but the direction is changing. One of the two ingredients is changing, and that alone is enough. The velocity will change. Even with a lock speedometer, this car's velocity is changing at every single instant. So now we have the complete picture. A velocity can change in two ways. The speed can change, that is what we saw on the straight road, or the direction can change, that is what is happening here. Either one alone is enough. And in the next part, we will take this curved road and actually measure how much the velocity changes. That is where the real physics begins. Alright students, let's continue. Now look at this carefully. I have a car moving along a winding road, a curved path. And here is the important condition. The driver keeps the speedometer steady. The speed is constant throughout the journey. Now, the question I want you to think about is this. Is this car accelerating? To answer that, let's mark 2 points on the path. Point A and point B. At point A, the velocity of the car is v1. And remember what we learned earlier. Velocity is always tangent to the path. At point B, the velocity is v2. Again, tangent to the path at that point. Now watch. The magnitudes are equal. Both arrows have the same length, equal to the speed v. But look at the directions. They are clearly different, and velocity is a vector. If the direction has changed, the velocity has changed. One more observation about this road before we calculate anything. At every point, the curve bends by a different amount. Near A, the bend is gentle, so the radius of curvature, RA, is large. Near B, the road turns more sharply, so RB is smaller. And further ahead at C, we get yet another radius, RC. So on a general curved path, every point has its own radius of curvature. It is as if, at each point, the car is momentarily moving along the circle of that radius. Now let us actually compute the change in velocity as the car goes from A to B. Change in velocity, delta V, is final velocity minus initial velocity. That is, v2 minus v1. And minus v1 simply means v2 plus negative of v1. Let me do this graphically. I bring both vectors to a common point. Here is v1, and here is v2. Same length, different directions. Now I flip v1 to get minus v1. and add it to v2. The closing arrow, from the tip of v1 to the tip of v2, this is delta v. And look at this carefully. Even though the two speeds were exactly equal, delta v is not zero. The change in direction alone has produced a change in velocity. And students, the moment velocity changes, there must be acceleration. By definition, acceleration is delta v divided by delta t, and strictly speaking, in the limit this delta t goes to zero. So the answer to our question is yes. The car is accelerating, even though the speedometer never moved. Write this down in your mind. Constant speed does not mean zero acceleration on a curved path. Next question, in which direction does this acceleration point? Take any point D on the path. At D, I can always split the total acceleration into two perpendicular components. One component along the velocity, tangent to the path. We call it the tangential acceleration. At T, its job is to change the speed of the car. The other component is perpendicular to the velocity, pointing toward the center of curvature. We call it the radial, or centripetal acceleration, R. Now apply our condition. The tangential acceleration is the rate of change of speed. At t equals dB by dt, but in our problem the speed is constant, so dB by dt is 0. Therefore at t is 0. The only thing that survives is the radial part, and its magnitude, r, equals b squared by r, which is the same as omega squared r. Here, b is the speed at that instant, and r is the radius of curvature at that point of the path. So think about it. On a sharp bend, r is small, and the centripetal acceleration is large. On a gentle bend, r is large, and it is small. That is exactly what your body feels when a car takes a sharp turn at speed. Now students, let us take the most important special case of what we did in the last segment. Instead of a general winding road, let the particle move on a perfect circle. Here is the circle, here is its center O, and here is our particle, going round and round along the path. And we keep the same condition as before. The speed is constant. First, the geometry. On the winding road, remember, the radius of curvature kept changing from point to point, but a circle is special. Take any point on it, and the distance from the center is the same. R here, R here, R here, R everywhere. One single radius for the entire path, and that is exactly what makes circular motion so much easier to handle. Now watch the velocity. At every instant, the velocity is tangent to the circle. So as the particle goes around, look at the arrow. It points this way, then this way, then this way. The length of the arrow never changes, because the speed is constant, but the direction is changing continuously. So in circular motion, the velocity vector is always changing. It never stops changing, not even for an instant, and by now, you know exactly what that means. If the velocity is changing, there must be an acceleration. Always, as before, we split this acceleration into two parts. The tangential part, at t, which is the rate of change of speed, dB by dt, and the radial part, r, equal to v squared by r, always pointing toward the center. Watch this arrow carefully as the particle moves. It keeps turning, so that at every single instant, it points exactly at the center. And here is the crucial point. This radial part can never be zero, because the direction of motion never stops changing. This gives us the two standard cases that you will meet in every problem. Case 1, uniform circular motion. The speed is constant, then dB by dt is 0, so the tangential acceleration is 0, but the radial acceleration, b squared by r, is very much present. Case 2, non-uniform circular motion. Here the speed itself changes, so now the tangential acceleration is not 0, and of course, the radial acceleration is also not 0, so look at the full picture once more. In any circular motion, uniform or non-uniform, the centripetal acceleration, b squared by r, is always there. The only question is whether the speed is changing. If it is, a tangential part gets added. If it is not, then the center-directed acceleration is the whole story. Students, let us now place the two cases side by side and study them properly. On the left, uniform circular motion. This particle goes around at a constant speed. On the right, non-uniform circular motion. Watch the particle on the right carefully. It is speeding up as it goes around. Same circle, same radius, but the speeds behave very differently. Take the uniform case first. The speed never changes, so the tangential acceleration is 0. The only acceleration is the radial one, pointing at the center at every instant r equals omega squared r, which is the same thing as v squared by r. That single, Center-directed acceleration is the complete story of uniform circular motion. Now the non-uniform case. The radial part is still there, r equals omega squared r, because the direction is still changing, just like before. But now the speed is also changing, so the tangential part comes alive at t equals dB by dt, the instantaneous rate of change of speed. So this particle carries two accelerations at the same time, one along the tangent and one toward the center. And how do we combine the two? They are perpendicular to each other, so we add them like vectors. Tangential this way, radial this way, and the total acceleration is the diagonal of this triangle. Its magnitude is the square root of r squared plus a t squared. And notice something interesting. The net acceleration in non-uniform circular motion points neither along the tangent, more exactly at the center. It leans somewhere in between. Now let me show you something beautiful, which will save you enormous time and problems. You already know the equations of straight line motion with constant acceleration s equals ut plus half a t squared, b equals u plus a t, and v squared equals u squared plus 2as. Now look at circular motion with constant angular acceleration. Alpha, theta equals omega naught t plus half alpha t squared. Omega equals omega naught plus alpha t, and omega squared equals omega naught squared plus 2 alpha theta. Compare them line by line. They are the same equations, letter for letter, and the dictionary between the two worlds is very simple. The angle theta is the angular position. Watch the radius sweep around. Theta simply keeps growing. It plays the role of the displacement s. Then omega, which is d theta by dt, is the angular velocity. It plays the role of v. And alpha, d omega by dt, which is also d squared theta by dt squared, plays the role of a. Tell every straight line problem you have ever solved, you can now solve again on a circle. Just translate the symbols. And so, students, we arrive at the final segment of this series. Everything we have built, segment by segment, comes together in one picture. Non-uniform circular motion. Here is the circle, here is the radius r, and here is our particle, a point on the path, moving along the circle and speeding up. Let us freeze it right here and read everything this picture has to say. At this point, the particle carries two accelerations. The first one is along the tangent, the tangential acceleration at t equals dd by dt. It exists because the speed is changing. This is the very thing we first met on the straight road, at the beginning of the series. The second one is along the radius, pointing at the center. The radial, or centripetal acceleration r equals omega squared r, which is the same as v squared by r. It exists because the direction is changing. This is the part the curve itself demands. And on a circle, it is never zero. And the total acceleration is simply their vector sum. Total A equals a t plus a r. Since the two parts are perpendicular to each other, the magnitude is the square root of a t squared plus a r squared. Look at the picture. The total acceleration leans between the tangent and the radius. This one diagram contains the entire chapter. If you truly understand this picture, you understand circular motion, not as a list of formulas to memorize, but as one simple idea, seen from different angles. Velocity is a vector. Change its magnitude, and you get a tangential acceleration. Change its direction, and you get a radial one. View both at once, and you get exactly this. Let us look back at the road we traveled together. In segment 1, velocity changed because the speed changed. In segment 2, velocity changed because the direction changed. In segment 3, we measured that change on a curved path and discovered the acceleration hiding inside it. In segment 4, we entered the circle, where the radial acceleration never sleeps. In segment 5, we combined both accelerations and learned the angular language of theta, omega, and alpha. And today, in segment 6, we put the complete picture together. That brings our series on circular motion to a close. Practice well, stay curious, and all the very best for your JEE.